Okay, so today we're going to be looking at concavity. Concavity and the first derivative, so some connections between that. So the graph of a differentiable function, y equals f of x, is number one, concave up. And concave up means that like there, so it has a little cut opening. This would be a symbol of concave down. So if you see a graph that does something like that, that's concave up, and that is concave down. It is concave up on an open interval if its derivative is increasing. A function is concave down on an open interval if its derivative is decreasing. Okay, so that's one way to determine concavity, is by the derivative of the function increasing or decreasing. We can also look at it from the second derivative, and we usually do it by this approach, but we need to be able to do it both ways. If a differentiable function at y equals f of x has a second derivative, so if it has a second derivative, then the graph of the function is concave up when the second derivative is positive. And it will be concave down when the second derivative is negative. So we have where the first derivative is increasing or decreasing. And we have it when the second derivative is either positive or negative. So these two approaches help us find concavity. And this is a big chunk of questions you're going to be asked to do. So here is our first example for this. Let's take a look at it. So here we go. I'm going to zoom out just a bit so you can see it all. So here we go. The figure right here, this picture, is a graph of the derivative. So I'm looking at the derivative of f. Okay, f is a twice differentiable function. It is on the interval from -4 to +5. The graph of f has horizontal tangents at -2, 1, and 4, and we can see that clearly because the derivative graph has zeros there. On what open interval or intervals contained in this interval right here from -4 to 5 is the graph of f concave up and increasing? And give a reason for your answer. Okay, so it's asking us to compare two things. So break it down one piece at a time. So the first thing we want to look for in answering this question, we want to know when it's concave up and increasing. So I know that f is increasing, and I'm going to abbreviate here. F is increasing when the derivative of f is greater than 0. And I know that f is going to be concave up, excuse me, did the wrong one, up when what? When the derivative is increasing. Okay, so we need to look at those two things. And so we want to find out, and looking at both of these scenarios, where they would overlap. Because I want concave up, and I want the function to be increasing. So we look over here, and we can see the derivative right here. And where is the derivative positive? Well, we can see the derivative is positive between -2 and 4, because if it's above the x-axis, it's positive, below the x-axis, it's negative. Okay? So first off, we're restricted to this interval right here. And in this interval, what I'm looking for concavity, concave up, is I need that derivative to be increasing. Okay? So I need this thing to be increasing. So where is that occurring? Where is f prime of x increasing in this interval from -2 to 4? Well, it's increasing here. It's decreasing here. It's increasing here. And it's decreasing over here. So I have two intervals where it is increasing. Okay? And so then I can take that and write my answer for this problem. So for the interval from -2 to -1, and the interval from 1 to 3 are the two intervals because, and then I have to state why I know, based off of the picture that I had here, because f prime of x is greater than 0 and increasing on these intervals. And that's how you would write this answer. Okay? This is what we were looking for. And this is my final statement and answer. Okay? Let's look at another example down here. Here I have a function h, which is x to the third minus 6x squared minus 7. What are the values of x where the graph of h is concave down? Justify your answer. So in this process right here, since I was given an equation, okay, in a function form, then I can answer this question for concavity. So what I need to do is I have to start off, I want to find h double prime. Find the second derivative. And then we're going to do the little number line and test regions. And I'll explain it when we do it. And then we're going to make sure we answer the question. Okay? And we have to use the proper format for answering this question. So let's start off. Find h prime. So we find the first derivative. So this would be 3x squared minus 12x. Then we want to find the second derivative. And now I have 6x minus 12. Okay? And using the second derivative for concavity, I want to know where the second derivative is positive or negative. So since I want concave down, I want to find out when this thing is negative. So the first thing I do is I set it equal to 0 and find out where it's equal to 0. And we got it is equal to 2. And then we do a little number line, just like we did for the other one. But this time we're going to be doing it with second derivative. 2 is where it's 0. And I'm testing regions to determine the sign of the second derivative. That's why I put that out here. And so we can just do numbers over here, plug it in into the second derivative. If I put it in a 0, then I'm going to have a negative value. And if I plug it in 10, I'm going to get a positive value. So there's my regions right there. Since I want to be concave down, when the second derivative is negative, then it is concave down. So we can see clearly right here, this is the region where h would be concave down. So that's what we write. The graph of h is concave down when x is less than 2 because h double prime of x is less than 0 there, so it's negative there. That was how I determined my answer, so that's how I would write it. And since I can find h double prime, I can use that. If I can't find h double prime, I can't really talk about this. I'd have to use it like I did up here, using the first derivative. Okay, so let's look at more definitions before I move on to the next example. So in this one right here, we're going to look at what's called points of inflection. What is a point of inflection? And it has several points of view. So the more points of view you know, the easier questions become. So a point of inflection is simply a point on the graph of the function where it changes concavity. So first things first, this point has to exist on the original function. Okay? Justifications involve asserting either that the first derivative changes from increasing to decreasing or vice versa. The second derivative changes sign. The first derivative has an extrema. Okay? All of these things right here show that I have a point of inflection. So depending on what information you have, okay, the easiest one is obviously the second derivative one. But the other ones you can do also. But so be aware of all three approaches to finding points of inflection. Points of inflection are extreme values of the first derivative. They are extreme rates of change. It is the fastest rate of change, okay, or the slowest rate of change, things like that. Graphically, if I look at this thing over here in this graph, why does concave down mean the same thing as decreasing slopes? Okay, why are the points of inflection extreme rates of change? So if you look at this thing over here, this graph I'm looking at, the slopes right here, this is concave down. There's a spot right here. Once I come around, the slopes are going to be decreasing. And the slopes are negative, but I'm coming from a 0 and I'm getting larger. There's a point in between here where it stops getting larger and then it's going to start getting smaller again because I have to get back down to 0. And it's that point is where the point of inflection is. Okay, the slope is the lowest here, remember, because we have negative slopes. And then over here is the same thing in the other direction. I have positive slopes over here. I'm coming from 0, they're increasing to this point right here, and then they have to start decreasing to get back to 0 again. All right, these are points of inflection in this scenario. All right, so let's look at an example of some things we're going to be doing with this, some ways the questions may be asked. All right, let's see. Let me move this so you can see it. Where does the graph of this y equals x minus 2 quantity to the 1/3 power have a point of inflection? Give a reason for your answer. Since I am given this equation right here, or this function graph, I can take it and use the derivative approach, which means I'm going to find the first and second derivative. So once I have that, then I can go into and find the second derivative. So that times that gives me a negative 2/9, x minus 2, lower the power by 1, that's now negative 5/3. And then you can look at it with positive exponents to help you see things. And this over here becomes a negative 2 over 9 times x minus 2 to the positive 5/3. And I wanted to see it this way because I need to find possible points of inflection. Possible points of inflection are when the second derivative is 0 or undefined. Okay? We want to look for possible points of inflection. When is the second derivative equal to 0 or undefined? Now again, possible points of inflection. These are not points of inflection, these are possible. When you set the first derivative equal to 0 and undefined, those are called critical points. Those are critical points, all of them. These are just possible ones. We have to confirm that they are ones, because the only way I can confirm that I have a point of inflection is if the second derivative changes sign. Okay? So looking at this, that's why I wanted to see it. So there is no value that will make this 0, but there is a value that will make it undefined. So I can see here that y double prime is undefined at x equals 2. Okay? So when I have that, then I can come over here and do the little number line region. Here's 2. Here's y double prime. I'm checking the signs for this. So taking the numbers over here, plug in 0. Okay, this all is going to be negative. Negative on the top. This will be positive over here. And if I plug a number over here, then this will be positive, and the negative here makes it all negative. Okay? So how do I express my answer here? There's a couple ways to do it. Here's one I'm going to write right here. So y double prime is greater than 0 for x less than 2. And y double prime is less than 0 for x greater than 2. Because I just basically stated, I cannot use this. I have to state what this is saying. That's why I had to write that. Because the second derivative changes sign at x equals 2. The graph has a point of inflection. There. So I had to establish the sign change, and then I state the sign change at that point, which makes it a point of inflection. So there's that right there. Okay? So there is our solution, the way you want to write it. All right, let's take a look at another example that they could ask you for. So over here, I got a graph x squared, a graph cosine of x. They are given. These two I gave you. Use the second derivative to explain why this graph, this right here, x squared plus the cosine of x, cannot be this graph. Okay? If I add these two equations together, explain using the second derivative why this cannot be the graph. Okay? So let's take a look at this. Here's an equation that I gave you. We can find the derivatives of that equation. So y prime equals 2x minus the sine of x. And y double prime would be 2 minus the cosine of x. Okay? So we're going through our argument here. I see this right here. And so we need to look at the signs of this thing. Okay, what's going on here? And I can see, because of cosine, remember the cosine goes between -1 and 1. So that's the only values I'm going to have is between -1 and 1. So the lowest number this thing can be would be -1, and 2 minus the -1 is 3. And the smallest, and that's the smallest this can be, the largest it can be is 1, and 2 minus 1 is +1. Okay? So we have a conflict here. What this is telling me is that this right here, the second derivative, no matter what, is going to be positive, no matter what x's I plug in. If this is positive, then that means the original graph must always be concave up, and there will be no points of inflection. But if I look at this graph is not always concave up. Concave down, bunch of points of inflection in here. So it contradicts, what we know to be true. And so that is our answer. So this one is not the graph of that. And you just simply write that out. So since -1 is less than or equal to the cosine of x, like so, x is between -1 and 1. So the values of the cosine is between -1 and 1. That's what I'm saying here. When that occurs, the second derivative is always greater than 0 for all x's. So this means that the graph must always be concave up and can have no points of inflection. Okay? So this is not the graph. And that's how you would look at it. So when you start doing stuff like this, start looking for those kind of things, because we have determined the signs of this, where it was 0, there's a bunch of them. But we can see that it's always going to be positive. There's a bunch of zeros for the cosine, there's not for this. This is always positive. Okay? So let's take a look at some other things before we go to the next example. Some misconceptions that people have. The second derivative need not be 0 in order to change signs. So here's an example. This is our cube root graph, and we know that this cube root has a vertical tangent here at this point right there. In this case, that's at 2. The second derivative fails to exist. This is my original function. I can take the derivative of, but it fails here. Okay, it can't happen here at 2. All right, but this is a point of inflection. Okay, so the second derivative is undefined. But remember what I told you. Okay, we check for the second derivative to be 0 or undefined, but the point of inflection must exist on the original function. So this is going to be the point of inflection. Just because the second derivative is 0, this does not mean it must change signs. So again, when we did that, remember I said very clearly, that when you do the second derivative equal to 0 or undefined, these are possible points of inflection. You still need to confirm them. And here's a couple of examples that kind of illustrate this. For this graph right here, it looks something like this. First derivative, second derivative, all of which are, fine. The second derivative is 0 at 0, but we can see that the concavity is not changing there. The signs do not change for this thing. So again, 0 would not be a point of inflection. The second derivative test. So we have the first derivative test, we have the second derivative test. The second derivative test uses critical points and the second derivative. So the second derivative test for extrema. If the first derivative at A equals 0, that makes A critical point. This is where the first derivative was equal to 0. Not the undefined, only the ones that make it 0. If I take those numbers, okay, and take that critical point and plug it into the second derivative, and if I get a positive answer, then I'll have a relative minimum there. If I take the critical point, okay, where the first derivative was equal to 0, and take that critical point number and plug it into the second derivative, and then I get a negative answer, well, then that function has a relative maximum there. Well, why is that? Well, if this is a critical point, this is the function f. If this is right here is where a relative minimum occurs, well, you can see that the graph is concave up. So I have a minimum when I have concave up, second derivative is positive, and I'll have a maximum when the function is concave down. Okay, so I have a maximum here, so then this graph is concave down. So I'll have a maximum here when the second derivative is negative for concave down. Notice we don't include critical points where the first derivative is undefined, okay? Because I can't plug in an undefined into the second derivative. I just can't do it. Another note, when I plug in the critical point and the second derivative becomes 0, okay? So if I take those critical points and I plug it in here and I get a 0, not a positive or negative, but 0, that means this test is inconclusive. You have to use another method. And usually what happens is we just drop down and use the first derivative test. Okay, very important to remember this. They're probably going to test you on the subtleness of this. Okay, so let's look at another example using this. So g is this function right here, 2x squared minus the natural log of x. X is greater than 0. Identify the x value of the critical point of g and classify that point as a relative max, min, or neither. So in this thing right here, I got to find the critical points. So we take this function right here, we find its derivative. So g prime of x is 4x minus 1 over x, and I need to set that equal to 0. Okay. I can also look to see where it's undefined. It's undefined at 0. But since I'm only defined for numbers bigger than 0, then that one undefined point does not count. So where is this thing equal to 0? And you can solve this out and work this all out, and you will get that you're going to get it at x equals plus or minus 1/2. Take a little bit of time in the video. But my domain is for x is greater than 0. So x equals -1 is out. So now I have only one point, and that is x equals 1/2. This is my critical point right here that I need to use. Let's find the second derivative. Take the derivative of this thing over here, and in doing so, you're going to get 4 plus 1 over x squared. Again, you can check that out for yourself. And then the second derivative test says take this point and plug it into this equation over here. Okay, and what do we get from here? All of this right here, all I care about, not the number, but what I care about is positive or negative, and this is going to be positive. So what it tells me is at these critical points, the second derivative is positive, which means I'm going to have a relative minimum. And so then we write our final answer. So g of x has a relative minimum at x equals 1/2 because by the second derivative test, g prime at 1/2 is 0, and g double prime of 1/2 is greater than 0. That is how you should write your answer, just like that. Okay? And so we have the last example right here is the information given in the table. Selected values for a twice differentiable function twice differentiable function h, and its derivatives are given in this table. Which of the following must be true? Okay? Which one must be true? Do I have an absolute maximum at -4? Is h concave down on this interval? Is h has a relative max at 7? Or is it none of the above? Okay? So let's look at each one of these cases. H has an absolute maximum at -4. Okay? Well, on this interval from -4 to 10, if I only look at that right there, okay, I don't know what's in between. Okay? I don't know is this all the zeros? I don't know that. So I don't have enough information to determine that one. Okay? H is concave down from from 3 to 7. Well, it may seem like it could be, but the problem is I don't know what's in between here. Does it go up and down? Okay? If it says it's concave down for this entire interval, I don't know if it goes back up or comes back down. I don't know if H does that. Okay? So I don't know if that's all concave down. So again, we don't have enough information. H has a relative maximum at 7. Is this a relative maximum at 7? Well, for that to occur, H prime at 7 must be 0. Yes. And H double prime at 7 must be negative. Yes. So there's our answer. It is answer C. H of x has a relative max at x equals 7 because by the second derivative test, H prime of 7 is 0, and H double prime at 7 is -4, which is less than 0. And that's the second derivative test. It uses both the first and the second derivative and the critical points to determine if you have those available to you and you don't have a picture. Usually it'll be in like a table format, things like that. Okay? So that concludes this video, and we'll do more in class.